Um, look, I assume that you can hear me right now. Can someone just type a message into the chat? And I can't see the chat. Apparently, only members of the team have access to the chat. So that's not going to be much good if you do. Is someone able to unmute their microphone?
We can hear you.
Ah, Cody, lovely. Alrighty, so folks, again, I don't understand why our Zoom meeting, which was scheduled to start 47 minutes ago, didn't happen. But how long can I have you for? I mean, do we agree that we simply run through to 1 p.m., which was the original sort of end date, end time, or do you want to sort of just work for 2 hours? What's the vote on that? Anyone?
Wouldn't it be dependent on the tutor?
Well, the tutor is just not here.
Oh, okay.
That's the issue. That we were supposed to be doing this over Zoom, right? But no one let me access the Zoom meeting. So look, I think an executive decision. I know that you have your own timetables beyond this 2-hour tutorial. So let's just work through until 12:50 p.m. this afternoon, which is in accordance to what the original 2-hour tutorial slot was all about. Yep.
Yeah, I think that makes sense.
All right. So my next test is I'm going to try and share my desktop now. And it looks like my desktop's being shared. Can someone confirm that you can see my desktop?
Yeah, I can see that. I think that
works. All right, folks. So we've got an hour instead of 2. So let's see what we can do. All right, so let's start this. So for those of you that have stuck around, good morning and thank you for your time. Let me just go over very quickly some of the stuff that we covered in last week's, just to make sure that everyone is in a good position to be able to sort of launch Matlab. So the first thing that I want to say is, for those of you that haven't installed the latest version of Matlab, which is R2024B, there is something that you will need to do to your older version of Matlab. We talked about this last week. That is that in your older release of Matlab, you will need to untick a checkbox, which by default prohibits you from opening Simulink models that were created in a newer release. So again, the bottom line on top is that for those of you out there that do not have R2024B as your Matlab install, you've got an older version, you will need to follow the instructions that are on the screen right now. Because if you do not follow those instructions, you won't be able to open the Simulink files that we're looking at this morning. All right, so this is just a repeat of what we covered last week.
Just taking a screenshot of that, but if I'm on 2020A, should I upgrade to a newer version?
So you're saying that you have R2020A installed, is that correct?
Yeah. It doesn't sound right to me either, but it's what my computer says.
Well, yeah, I would definitely encourage you to install R2024B after this tutorial.
Thank you.
During this tutorial, if you do want to follow along, you'll need to follow the steps that were in that slide. Alrighty, so the other sort of repeat is I assume that you also have the zip file that we downloaded together last week, and you've already sort of unpacked that. But that's the other resource that you will need for today. So let's start. So what I'm going to do is I'm going to launch my Matlab 2024B. So if you're following along at home, I'd definitely encourage you to do the same. And for the gentleman that was on on the line literally just a minute or so ago, you'll be able to confirm whatever release yours is, that as soon as your Matlab launches, you'll see in the upper left-hand corner, right next to the little sort of thumbnail icon, you'll see the release of your installation. Alrighty, so assuming that at home you've been able to launch your installed version of Matlab, now what we're going to sort of do is we're just going to interact with MATLAB's sort of folder panel, and we're just going to sort of in MATLAB navigate to wherever the folder was that you downloaded the zip file. So I'm just going to start on my C drive, and then I'm going to go to this folder, and I'm going to double click here. So this is where I've sort of transferred the zip file, and I'm going to now unpack it, which was one of the things that we actually did a week ago. So many of you have probably already done this and don't need to do it obviously again. But I will be starting from scratch. And I am issuing the unzip command in the MATLAB desktop. Just be careful that if you are doing this exactly with me, whatever the name of your zip file is, you'll need to type that in. So by doing that, we now have a folder We now have a folder which contains today's workshop examples. So again, I'm simply going to double click on that unpacked main folder. And now it reveals sort of the internals of what was in the zip file, which was 5 case study examples. So the 2 examples that we did last week was this one, the spool on the truck bed. And I think we also did one of the virtual labs from memory. I think it was the principle of impulsive momentum. So we did that last week. So today, as much as possible, within an hour, we'll play with the pipe pendulum. So that will be today. And we'll also try, time permitting, to do the other virtual lab, which is a study on determining the kinetic coefficient of friction. But look, let's start. So what I'd like you to do is just navigate into the pipe pendulum folder. So just double click on that pipe pendulum folder. And again, if you're just trying to, as much as possible, sort of see exactly the same thing on your screen as you see on mine, then a nice little configuration setting is to click on that icon, choose group by, and then choose group by type. And that'll simply collect all of the script files together, all of the Simulink files together. It just makes it easier to find it in MATLAB's folder panel. Okay. So let's have a look at what we've got. Unfortunately, there is not a start here file. So we're just going to have to sort of apparently go with the numbering logic. Let's sort of open this file first. It's called task number 1. So find that file, and in order to open it, just double click on that file. Alrighty. So folks, in all this chaos of this morning, I forgot to sort of give you a reminder on what we really want to accomplish today. So all we want to do is just to make sure that you are comfortable and confident to open these case study files and to be able to run them. Because in your final semester project, you'll be asking to do something along the lines of do some hand calculations and then sort of compare those things to what these MATLAB and Simulink case study files produce. So bottom line on top, today we just want to make sure you know how to open files, run them, and play with them. So let's talk about this very first task. So this case study, it revolves around studying a simple pendulum. So if you're looking for a real-world practical application, you can think of a concrete pipe that's being lifted by a forklift. So imagine the canvas straps that get threaded through the pipe and then over the tines of the forklift, and we've now got a forklift that is lifting this thing and potentially sort of moving it to some location. So let's just get comfortable with what this thing is. We've obviously made an idealization for it, but let's just make sure we're really comfortable. So in each of these sort of diagrams, we're sort of doing a drip feed of what's important. I'm going to sort of start with the middle diagram. So we clearly have L as being the parameter that represents the length of the pendulum arm. We have the radius of the concrete pipe. We have the mass of the concrete pipe, and we have the mass moment of inertia of the concrete pipe. Something that I want to sort of say here is we're going to make the assumption that the length, that the pendulum arm itself, its mass is negligible in comparison to the mass of the concrete pipe. So the idealization is that the pendulum arm, it's still a rigid component, but the pendulum arm is we're going to treat it as being a massless component, clearly an idealization. The other item that I just want you to sort of focus on is this is a single degree of freedom system, and that degree of freedom is the angle theta between the vertical datum line and the pendulum arm. And if you just look to the very right, the very final piece of information that we're trying to convey is just some simple geometry that specifies the X and Y positions of the center of mass of the pendulum. So that's really, really simple stuff. So we've got a suspended concrete pipe pendulum. Let's see if we can sort of first of all derive the equations of motion for this thing. So as I sort of scroll down the script to this very first section, let me sort of get you orientated. So I'd like you to sort of scroll down until you get here. And again, just click anywhere inside this part of the script. And when you've done that, you'll see that over on the left-hand side, there's a little blue vertical strip. And the fact that it's blue, it's giving you feedback that this is the currently selected section in the script file. Now, that other blue strip, besides giving that nice bit of visual feedback, if you click on that blue strip, it will run the code just in this designated section. So I'm going to ask you to do that right now. So once you've clicked in this section, move across to the blue strip. You'll see that your mouse cursor changes from a pointer arrow to a finger clicker. And as soon as you get that icon, that change, just click on that blue strip and it will run the code in that strip. So let's talk about what that code is. So in this very, very first task, which is about using Newton's second law to derive the equations of motion for this pipe pendulum, we're actually going to use some of MATLAB's symbolic computing capabilities. So ordinarily, when people think about MATLAB, they envisage solving numeric problems like defining numeric matrices, computing the inverses of a matrix, etc., etc. But MATLAB also has some very strong symbolic computing capabilities. And if you're not quite sure as to what I mean by symbolic computing, you will by the end of the next few minutes. But if we just sort of look at lines 1 to 4, you'll see that the first 4 lines of the script, we use this keyword sims. And that keyword sims allows us to declare variables as being symbolic. So here we've got a couple of those geometry variables that were obviously sort of on our diagrams just above the screen. And we've also got some other variables, the degree of freedom variable, Rx and Ry will become apparent what they are in just a moment. But anyway, we've created some symbolic variables, and we'll be using these symbolic variables to help us implement Newton's second law. So just scrolling down the script, let's click in the next section. And the next section is called Compute the Acceleration of the Pipe COM. Folks, can you just mute your microphone? There's a little bit of background noise. Can you please mute your microphone?
Oh, yeah.
Lovely. Alrighty, so we're going to be using Newton's second law in just a moment. So clearly F equals ma, and we need to be able to sort of incorporate acceleration. So let's kind of get ahead of that, and let's just use symbolic computing to compute the acceleration vector of the center of mass. So let's execute the code in this new section. And let's see what we've got and what was produced. So you can see that we're creating a vector that defines the x and y coordinate of the center of mass. And then we're invoking the diff function to compute both the first and second derivatives of that position vector. So clearly it's the second derivative that gives us the acceleration of that center of mass of the concrete pipe. And after executing this section of code, here's what the acceleration vector looks like for our concrete pipe. Now again, just trying to sort of get your mind in the right frame. This problem is a really simple one, and everything that we're sort of showing you with symbolic computing, you could have easily have done with pen and paper. But the workflow that we're about to go through, it scales really nicely for much more authentic and more complicated systems. So the reason that we're demonstrating this workflow is so that you know about it, and when the time comes, you can hopefully implement it for bigger problems. But nonetheless, we had the center of mass of our concrete pipe, and we've used symbolic computing to analytically compute the acceleration of that concrete pipe center of mass. So that's done. Let's continue scrolling down the script. So given that we want to sort of implement Newton's second law, we go into our stock standard training. In order to do that, we isolate every rigid body in the system. In this case, there is only one rigid body. And then we draw all of the externally applied forces that are acting on it. So I'll just get you to sort of stare at the free body diagram for this concrete pipe. Remember the arm of the pendulum is rigidly attached to the concrete pipe. So the forces acting on this system, you have the reaction forces Rx and Ry at that pivot point, and you also have the force of gravity, Mg. So that's a free body diagram. All right. So if you're comfortable with that, writing out Newton's second law is going to be pretty easy. It's a pretty simple thing. And here it is in the next part of the screen. So we'll take the information in the free body diagram, and we'll just use it as we write out Newton's classic F equals ma statement. Now the significance of that is when we implement this in symbolic computing, this is what it looks like on lines 15 and 16 of the script. So let's just stare at this. I mean, don't let the familiarity sort of distract you from just focusing on what you're looking at on the screen. So here's the syntax. We clearly have the left-hand side of Matlab of Newton's second law, m times the x component, and then on the right-hand side we have the sum of all of the forces acting in the x direction. And you'll see that the way that we make the statement that the left-hand side is equivalent to the right-hand side is we use that double equals sort of syntax, and that left-hand side equals right-hand side equivalence is then simply assigned to a Matlab variable. We do exactly the same thing for the vertical direction. And I'll get you to run this section now. So again, just clicking anywhere, moving over to that blue strip that's on the left-hand side, and just running it, clicking it. So as I sort of hover my mouse cursor over, say, one of these Matlab variables, you can kind of see, hopefully it's coming across, you can kind of see we can sort of see the results of what we've just produced, this x direction acceleration. And you can see that inside it, we have the acceleration terms that we computed earlier. That's very nice. So they're two of the Newton equations. And there is a third one that we can sort of write out as well, and that's the angular version of that second law. So the sum of all of the moments about the center of mass is equal to the mass moment of inertia times the angular acceleration. And again, we start with a free body diagram, and then we sort of write out what the sum of all of the torques are acting about that center of mass. And the symbolic computing implementation is sort of shown on line 17, all right? Again, if I sort of, well, I don't need to hover my cursor over it. We actually echo the contents of that third equation on the right-hand side of the screen. So we've got three equations, and what I'm going to do is I'm just going to scroll down to the next section called Pause and Ponder. And once I've clicked inside Pause and Ponder, I will run this section of code. And I'm just going to change my view so that you can sort of see it. So here we are. Here are the three equations that we've just sort of derived from Newton's second law. And right now, I'm guessing that a number of you on the call are feeling a little bit anxious because this is a single degree of freedom system, and yet we clearly have produced three equations of motion. And once you've sort of gone past that anxiety, you can hopefully clearly see that two of these equations, implement the motion constraint at the pivot point. The pivot point cannot move, so we need two constraint equations. And a lot of the time in early year engineering, a lot of effort is put into removing those forces and sometimes moments of constraint. So you can clearly see that if I took this expression for Rx and substituted it into here, and if I took this expression for Ry and substituted it into here, you'd end up with a single second order nonlinear ODE where all of the constraint forces have been removed. But we're not going to do that. We are not going to do that because you're mechanical engineers, and the constraint forces acting at the pivot point are often an important design component. I mean, we have clearly time varying forces at that pivot point, and that means that there are stress cycles. When you have stress cycles, that means fatigue life becomes something that ultimately needs to be considered in overall design. So we will not be removing constraint forces. We will be sticking with these three equations right now. So as I sort of scroll down the script, I'm going to put it to you that the three equations that we have, the three unknowns that we're probably interested in are the angular acceleration of the pendulum and then the two reaction forces at the pivot point. They're our three unknowns. So what we'd like to do now, as I continue to scroll down, is let's get Matlab to rearrange those three equations that we were just staring at. Let's get Matlab to rearrange those three equations into this form: AX equals B, where the X vector is simply our vector of desired unknowns that we would like to solve for. So this lovely little symbolic computing equation, function, equations to matrix, it will just rearrange those three things into that form. So let's run this section of the script, and you can kind of see what those A and B matrices are. And for really big authentic systems, these A and B matrices are all we need to now numerically solve for those nonlinear ODEs. But given this is a really simple system, let's just symbolically solve for our unknown vector. And when we do that, it's just using MATLAB's stock standard / operator. So we'll now get symbolic expressions for these three things. And here they are. You can sort of see that the angular acceleration is this thing. And then the two really long expressions underneath it are the time varying expressions for the reaction forces Rx and Ry. So that's nice. Let's keep scrolling. So now that we've sort of, we've derived the equations of motion, I want to get them in a form that makes it really easy to numerically solve those ordinary differential equations. Now, MATLAB can solve ODEs, but Simulink can solve them as well. And given that we're going to be moving into Simulink in the next minute, let me show you how you can automatically convert your symbolic expressions, your expressions for theta double dot, for Rx and Ry. We can automatically convert those symbolic expressions into a Simulink block. Then we can subsequently use that Simulink block and ask Simulink to solve the ODEs. But here's the first bit of the secret sauce. there is a symbolic computing function called Matlab function block. What Matlab function block allows you to do is it allows you to specify your symbolic expressions, theta double dot, Rx and Ry, and it will then automatically convert those expressions into a Simulink block. So let me sort of get you to run this section. So let's click on it and then click on the blue strip. And if this is the very first time you've invoked the Matlab function block function, which in turn launches Simulink, this might take a minute for you. I'll give you just a minute. But when you run that section, here's the thing that gets produced, this little yellow Simulink block. You can sort of study it and you can sort of see that it's got a bunch of inputs. Some of them, no doubt, are time invariant. They're constants. Some of the input signals, such as theta and theta dot, clearly they're time varying. The block apparently uses those inputs to subsequently compute the time varying signals for theta double dot, the time varying Rx force, and the time varying Ry force. When I double click on this little Simulink block, sure enough, it was automatically created today, the 5th of May at 12 minutes past midday. And you can see that sure enough, it just implements the expressions that we had for theta double dot, Rx and Ry. So the real feel-good moment is it doesn't matter how long and lengthy these symbolic expressions are. You've now got a mechanism to automatically convert them into a Simulink block. Again, which is really exciting when you're studying much more sophisticated industry size sort of problems. So all I really want you to sort of just acknowledge is we started out in this task 1, drawing our free body diagrams and then writing out Newton's second law. We implemented those equations using symbolic computing. We got symbolic computing to sort of rearrange those equations and then ultimately to automatically convert those symbolic equations into a little yellow Simulink block. So that's task 1 done. In the next task, we'll look at how we can get Simulink to numerically solve this system of ODEs. All right, so I think I'm done with this. I'm just going to close that Simulink file. And the next thing that we're going to do is we're just going to click on this link, task 2. So if you're following along at home, I'll ask you to click on that hyperlink, task number 2, simulation. Now, best practice, before we start each of these separate tasks is to clear the contents of your workspace. So I don't know where your workspace panel is in your Matlab desktop, but if you look at my screen, you'll see that my workspace panel is over on the right-hand side. And we clearly have a whole bunch of the Matlab variables that were produced during that task 1 script. So a really easy way just to clear the contents of that workspace is just to click on the Home tab sheet of the Matlab desktop and then look for an icon called Clear Workspace. If you click on that Clear Workspace icon, it should delete all of those task 1 variables out of your workspace. So let's do that. That's a really good best practice. Alrighty, so on my computer, my workspace is nice and clean now, which is hopefully what you're doing as well. All right, so task 2. Apparently in task 2, we are now going to numerically solve those ODEs that we derived for this single degree of freedom concrete pipe pendulum. So just scroll down the script, and what do we got? So apparently, this is where we finally define some numeric values for some of those system parameters. So you'll sort of see that we're specifying, for instance, the length of the pendulum arm. It's 0.25 meters. The pendulum mass apparently is 700 kilograms, etc. So unlike the previous task, what I'm going to get you to do here is let's just run the contents of this script in its entirety, because ultimately what I want you to do is to start playing with the Simulink model that gets opened when we do that. So let's just click on the Live Editor tab sheet within your Matlab desktop, and then come across to the biggest green triangle that you can see that should have the word Run underneath it. And then click on that Run icon, and it will run every section that is in your script from top to bottom. So please click on that Run triangle. Now I'm hoping that when you do that, this is the Simulink model, Simulink file, excuse me, that appears. So this Simulink file actually does two things. If I just sort of remind you of some of the really basic file navigation shortcut keys, if you open this Simulink file and it looked like you were staring at it from 10,000 feet above the ground, or alternatively, if the Simulink file opened and you've got your face pressed against the screen, neither of which are satisfactory, then the way to sort of make the file occupy the model occupy full screen is just to click anywhere in the white canvas of the Simulink file, and then hit the spacebar key on your keyboard, and that should make everything fit nicely into full screen view. So there are this Simulink file that we've opened. It actually includes two implementations of this concrete pipe pendulum. The yellow implementation, which I'm referring to as the Brain-Newton implementation, and also the green implementation, which I'm calling the SimScape model. And whenever you've got two different ways of doing the same thing, it's always reassuring that when you compare those two different ways, that they produce the same answers. And that's what we're going to be doing in this example. So let's have a look at the Brain-Newton model, the yellow model first of all. So you should be able to sort of see some tab sheets embedded within your Simulink editor. So just click on the Brain-Newton model tab sheet, and that should take you inside the contents of this yellow subsystem block. So when I do that, again, once it appears, I'm just going to by default hit the space bar. And here is where we would have dragged that little yellow block that we produced in task one. We'd paste it in and we'd wire it up. If this is the very first time that you've seen how Simulink can numerically solve ODEs, let me sort of give you the 30-second sort of summary. So Simulink is all about solving nonlinear dynamic systems. And one way that it can do that is if you define what an ordinary differential equation is, you can use Simulink's integrator blocks to then integrate those derivative terms. So here's how Simulink works. Say we've got this signal wire called theta double dot. Yep. We pass it through an integrator, and you know what happens when you integrate theta double dot? It's not a trick. What comes out of the integrator is theta dot. Yep. And if we take theta dot and we pass it through an integrator, you know what happens, right? Yeah, you get theta. So these sort of integrator blocks are at the very heart of how Simulink is able to numerically solve nonlinear ODEs. And yes, you're exactly right that it kind of looks like there's a feedback mechanism in the way that it does that, because if you follow the signal wires coming out of those integrators, you'll see that they're making their way back into the little yellow block. That's exactly what we need. So this is one way of getting Simulink to solve this system. In fact, look, at this point in time, I'd like to sort of just get you to click on that green run button, and let's immediately ask Simulink to solve this system of ODEs. Just click on that round green run button. When that happens, a little CAD viewer will pop up on your screen. Let's just forget about that for the moment, because that's in part 2 of our conversation. So I'm hoping that you've all been able to hit that green run button, and let's have a look at the results that have been produced. So let's double click on this pink oscilloscope block. The name of this oscilloscope block is called scope_Newton. So when you double click on that pink oscilloscope block, let's have a look at some of the time series results that have been produced. And here they are. So in all of these axes, time is on the horizontal axis. So you're looking at the time varying signal for theta double dot, the time varying signal for theta. The one at the bottom is clearly the time varying signal of theta. And then on the right-hand side, you can see the 2 axes that show the time varying reaction forces, Rx and Ry. So folks, congratulations. Just so that the significance of what we've done together hasn't passed you by, in task 1, we derived the ordinary differential equations for that concrete pipe pendulum. And we got the symbolic computing toolbox to automatically convert those equations into this yellow Simulink block. We've now asked Simulink to numerically solve those ODEs. And we're now staring at these time series plots that show that numerical solution of that system. Very nice. Well done. Well done. So if I now sort of climb back to the root of this Simulink file, which you can also do by clicking on this tab sheet. You'll see that in this Simulink file, not only did we include our brain-derived Newtonian model, but we've also included an alternate way of also modeling and representing the concrete pipe pendulum. And that alternate way of modeling is done using something called SimScape. So if you're kind of curious, you can click on this tab sheet, SimScape model, and by clicking on that tab sheet, it will take you inside the SimScape subsystem. Once you get in there, make sure you hit the space bar. So this is an alternate way of modeling that concrete pipe pendulum. All right. Just very, very quick. If I sort of double click on the pipe block, this is where we specify that this block represents the concrete pipe. Yeah. All right. So let me go back to the root level of the model again. So we've got our brain solution to solving the dynamics of this system. And we've also got the SimScape solution. And this is where I'm sort of going to come back to that CAD viewer that popped up onto the screen when we hit the green run button. So this CAD viewer, it actually pops up automatically whenever you have SimScape multi-body blocks within a Simulink file. So this CAD viewer appears because of this Simscape implementation. And the really nice thing about this CAD viewer is it's got lots of nice sort of interactive controls. Down at the bottom of the viewer, you can click on the playback controls that actually give you an animation of what this mechanical system is doing, which is just sort of swaying side to side. You can sort of click on some of the icons in the top of the screen, which hopefully are quite intuitive, and you can sort of change the viewing angles and so forth. So, all right, we've got the brain Newton model, we've got the Simscape model. I'm really hoping that these two different ways of modeling this produce similar simulation results. So let's click on the comparison tab sheet, compare. Let's click on this little guy. Once you get into that compare subsystem, hit your space bar. And inside this compare subsystem, you'll also see another one of those oscilloscopes. So let me sort of double click on this oscilloscope. When we do that, we get very, very similar looking time series plots that we had before. However, each of these axes now has two data sets plotted in them. So if I kind of just use my my magnifying glass to sort of zoom in, so let me click on that magnifying glass. And now I'm just going to sort of zoom in on just one of these. And after doing that a few times, you can see that we've got a yellow data set. That would be from our yellow Newton model. But we've also got simulation results in the way of these green dots, and that would be from our green Simscape model. So the sort of conclusion is that our Newton model is producing simulation results very, very similar to the Simscape model, which is quite reassuring. To bring the oscilloscope plots back to full view, this is the icon that you want to click on. Alrighty. So I think we're done. We're finished with task 2. So task 2 was simply about numerically solving the ordinary differential equations that we had derived in task 1. And it was also about sort of giving you some validation that the response of the Newton-derived model, its response was very, very similar to an alternate way of modeling the exact same system using something called Simscape. So I think we're done. I think we're done with task 2. So we can sort of close this guy. Folks, the remaining the remaining 2 scripts that are in this folder, they're called task 3 and task 4. Let's just open one of them. Let's say task 3. So in each of these additional tasks, they present to you a very slight variation of this concrete pipe pendulum. For instance, the task 3 script talks about a pendulum where the pivot point is mounted on a bracket that potentially can slide backwards and forwards. So if you'd like to explore what happens when we incorporate that sort of dynamics into our model, well, let's just run this script. I'm just going to move up to the green run triangle. I'm just going to run the script in its entirety. It's going to open up a Simulink file that only has a Simscape model in it. And we can sort of run this, and we can kind of see the resulting simulation. So I'll leave it to you to read in more detail the commentary that is inside the task 3 script, and you can sort of explore that on your own. All right, so that's just a time check. So apparently we have 20 minutes left. So this has just covered this case study, which is the pipe pendulum. Let's go back to the root folder, and I'm just on the way. I'm just going to clear my workspace. So we've just finished looking at this guy. So the next case study in the remaining 20 minutes is we're going to look at this virtual lab called pendulum impacting a block. So I really need to make sure that you're comfortable being able to open the files and run the files for this virtual lab. So let's navigate into this pendulum impacting block folder. Alrighty. So if you're following along at home, I'm hoping that your present working directory is this one. And when you get yourself into that present working directory, you should see these files. And on this occasion, there is one of those start here, please files. So let's just double click on this start here, please file. Let's see what it's got to tell us. Alrighty. So in this virtual lab, this is the mechanical apparatus that we're going to sort of explore. It consists of a pendulum, which is allowed to swing, and the pendulum collides with a block that is resting on the table. And due to that impact event, the pendulum ricochets and the block, is sent flying across the table. So this is the apparatus that we're going to play with. And you'll see that just like we did before, we can parameterize this apparatus. Let me just point out a couple of those things. We have the length of the pendulum, we have the mass of the pendulum, and we also have the block. So we're able to sort of specify that the mass of the block that's on the table. As I sort of scroll down this start here script, apparently there are 3 tasks that we're going to do. So let's have a look at each of those in turn. So I'll get you to click on task 1 first. Let's see what that's about. So task 1 is nothing more than getting you familiar with the Matlab variables that we've used to parameterize this apparatus. So as I just sort of scroll down the screen, I get to the instructions. Well, apparently instructions are, look, just run the script, man. So I click on the live editor tab sheet. I then look for that big green run triangle, and I just click on it. And as I sort of scroll down the script, you'll sort of see that embedded within this script, we've got the capacity to sort of specify values for some of these important parameters that characterize our mechanical apparatus. For example, you'll see that there's a slider bar for specifying the mass of the pendulum, the length of the pendulum arm. There's a slider bar that allows us to specify the mass of the block that's on the table. Let me sort of scroll down to the bottom of this task 1 script. That's going to get us to next steps. So at the very bottom of the script, you'll see there's a next step, and there's a little icon, a link, pardon me. There's a link called task 2. So let's just click on task 2. Let's see what that does for us. So the task 2 script opens up. Let's scroll down the screen. It's reminding you of what your prerequisites were. So let me just double check on my system. Does my workspace look like that? Yes, it does. That's because I ran task 1. Thank you. Then the instructions say, do not run this script by clicking the run button. Okay. And apparently there's a little video that you can watch. But as I scroll down to step number 2, it's gonna say, hey, why don't you just click this button? That's gonna open a Simulink file. So let's do that. Let's click on that button. So when you click on that button, here's the model. Here's the model that sort of opens up. If it looks too small, if it looks too big, just click anywhere on the white canvas and hit the spacebar. So, all right, the model opened, but I kind of feel that there was a little bit more instruction that we had to read. So yeah, apparently in this task 2 script, there are 2 experiments that we need to do. So the first experiment, it involves sort of specifying that the pendulum mass should be 5 kilograms, the pendulum arm should be 0.5 meters, and the block that's on the table should be 3 kilograms. So in order to make those changes, we need to go back to our task 1 script. We need to interact with those slider bars. So that's what I'm going to do. I'm just going to click on that little link. So we're back now to the task 1 script, and I'm going to scroll up to the top. And according to the instructions, we need to dial in 5 kilograms for the pendulum mass. The length of the pendulum was 0.5, so I don't even need to change that. And I need to make sure that the block was also dialed in at 3, which just happens to be where it was anyway. So you need to make these changes. 1, make sure that's 0.5, and make sure that's 3. So once you've made those changes, let's go back to the Simulink file, and let's just click the Run button. Let's run our simulation. So when you run your sim, we've got results that are not entirely unexpected. All right. So we have this really heavy pendulum mass. It's got quite a lot of kinetic energy, and it collides with the green block that's on the table, and the block gets shot across the table. All right. So what else does our script in task 2 tell us? What else are we supposed to note? We're supposed to note that inside the model, there's a subsystem called data logger. And inside the data logger subsystem of our model, there's one of those little oscilloscope blocks that we can sort of look at. So let's go and find that data logger subsystem in our Simulink file, and let's then open the scope. So here's my Simulink file, and here's the data logger subsystem tab sheet. I'm just going to click on that, and I'm going to hit the space bar. And here's the oscilloscope that we were supposed to double click on. So once you've found that oscilloscope, just double tap on it. That should open it up. And when you open your oscilloscope, the time series traces have been color coded. Green is obviously the data for the green block, and red is the data for the pendulum bob. So let's get you really comfortable with what these time series plots are. So this first one, as its title suggests, this is a time series plot that shows the position of the green block. You can kind of see that for quite a few seconds in the simulation, it was at position 0, horizontally, and then it continued to sort of move until it came to a stop, right? The other green axis is the velocity of the horizontal velocity of the green block. You can clearly see the impact collision event causes almost a discontinuity almost in the velocity. It went from being from a standstill to almost instantaneously having an initial velocity. And if you stare at that velocity time series profile long enough, you'll see that the velocity seems to decrease in a really nice linear fashion until ultimately the velocity comes down to 0, which means the block is stationary once again. So we've got our 2 green traces, which are for the green block. If we now look at the 3 red plots that are on the right-hand side, well, these red plots are showing plots of the pendulum bob. Let's just have a look at them. So this top one sort of shows the vertical position of the pendulum bob. According to some reference datum, the pendulum was initially approximately 0.5 meters above the datum. It then swung down, and you can sort of see the series of swaying, oscillating sort of events that the pendulum experienced. The next trace is the horizontal, the x-axis velocity of the pendulum. So this is that. And the last one is just sort of showing what the magnitude of the pendulum's velocity is versus time. All right, so you know where to find the scope block, and you know what the meaning of these time traces are. Let's go back to the script. So I think there was one more. There was one more experiment that we needed to do. And that experiment was, well, let's go back and let's significantly reduce the mass of the pendulum. Let's dial it down to only 1 kilogram. We'll keep the other 2 parameters at the same values. So let's go back to our task 1 script. Just click on this link. And let's grab that slider bar and let's move it over to 1. So for our second experiment, the 3 parameters that we want to make sure have been dialed in correctly is 1 for the pendulum mass, 0.5 for the arm of the pendulum meters, and 3 kilograms again for the block that's resting on the table. Once you've dialed these 3 parameters, let's go to our Simulink file and let's hit the run button again. We kind of bring our animation viewer back to screen. Let me just go to the playback and let's watch the replay. And you know, with less sort of kinetic energy within the pendulum bob at moment of impact, clearly the green block, you know, we're expecting it not to slide as far as it did in experiment 1, and we're sort of seeing that visually in this animation viewer. If we go to that scope block again and just bring up what it looks like this time and have a look at it. Clearly the final resting position of the green block, it didn't slide as far. It only moved around about 0.28 meters in this second experiment. All right, so that's experiment 2 done. We can go back to the script and let's see what it wants us to do now. So after you've done experiment 2, we're actually going to analyze the time series data that we've measured from experiment 2. So let's click on that task 3 hyperlink. So here's the task 3 hyperlink. And folks, we only have 5 more minutes together, unfortunately. So what I'm going to ask you to do is I'm going to ask you to simply run this task 3 script. Just run it, okay? This will run the script in its entirety. you will need to review this task 3 script in more detail on your own. But after running it, let me just sort of scroll through it, and I'll just call out what it's done for us. So what it's done is it's brought in the simulation data from experiment 3. So hopefully as I scroll down the script, you'll see very, very similar sort of plots to begin with. So this time series plot looks very familiar to you, doesn't it? It's the position, the horizontal position of the green block. It's also the horizontal velocity of the green block. We saw this within the Simulink model. We'll keep scrolling down. When we actually interrogate the data that is in that time series plot, we can answer the question, how far did the green block actually slide? And we can also answer the question, for how many seconds was the green block actually in motion for until it came to a stop? So we can kind of answer those two really basic questions just by interrogating these two time series plots. We can do a similar sort of plot of some of the red pendulum bob data, again, plots that we sort of saw in the Simulink file. When we sort of do that, we can also pull out some really fundamental sort of attributes out of those plots. We can answer the question, what was the starting height of the pendulum? We can answer, after the collision event, the pendulum bounced back and then it came to a halt. When it came to a halt, what was the height of the pendulum bob? So we can sort of answer these basic questions. What we're going to do now is we're going to use these measured quantities to compute the coefficient of kinetic friction. Yeah. So as I said, in the interest of time, I can't go through each of these steps in detail with you, but I'm hoping that you're comfortable enough to sort of review the commentary that is in these scripts. But you'll see what it does is it sort of takes a snapshot at 3 or 4 moments in time. For example, at time t equals 0, when I just released the pendulum, what can we sort of deduce about the kinetic energy of the pendulum bob? At time t1, the moment of impact, what can we sort of talk about the transfer of energy from kinetic to potential for the pendulum bob? So I'll let you sort of review this, all right? And the ultimate sort of conclusion is that by just focusing on positions and durations of quantities that we can measure from our experiment, lo and behold, we actually get ourselves to the point where we can use Newton's second law applied to the sliding brick. We can confirm that there is a constant deceleration acting on that green brick. And that's why the velocity profile, if you recall, was a nice linear decreasing velocity profile. And in conjunction with some of the measured and derived quantities, we can now get ourselves in a position where we can actually compute the kinetic coefficient of sliding friction. And the value of that coefficient of friction is 0.304. So taking some measurements, taking some fundamental energy principles, the principle of work energy, the principle of impulse and momentum, and combining all of those things, we've now got ourselves to this. We believe that for this apparatus that we've just interacted with, the kinetic coefficient of sliding friction is 0.304. And that's a really, really good thing, folks, because if I go back to my task 1 script, it actually turns out that the model that we interacted with really was configured to implement a 0.3 kinetic coefficient of friction. So it's really reassuring to know that we can go from measurements, implementing a couple of engineering principles, and they all converge to what we expect, which is a really nice feel-good moment. Okay, we have unfortunately run out of time. I'm hoping that was a nice walkthrough of the files associated with this particular virtual lab, and that you're also now confident enough to be able to go back, open them, and redo what we've just done together over the last sort of 20 minutes. So folks, again, apologies. I do not know why our Zoom session did not start at 11 a.m., but that's something to be resolved later. Thank you very much for your time this morning, and I wish you good luck on your final semester project, which revolves around the 4 case studies that we've reviewed together over these last 2 weeks. So thank you very much, everyone. And look, if there is a question, I think maybe we can spare 2 or 3 minutes of questions. If not, I'll let you go and get ready for your next lecture.
Thank you.
Lovely. All right. Have a good day, everyone. Thank you. Bye-bye.